Hi there, welcome back. We're now going to do the very exciting part of this restoration, and that is to find out if this thing does what it's meant to do. In other words, does this thing act as a radio? We know it acts as an amplifier because we've tested the audio section, the AF section. We know the preamp is working. We know the power amp section is working. We know the power supply is working. We know the output transformer is working. Now we need to know if this thing actually receives anything. And the first stage is going to be the AM section, so long wave, medium wave and short wave. If we got that working, sort that out, and then we'll do the FM section. Now the FM section, if you recall, has a burnt out resistor at the bottom down there, feeding, it's the power supply feed to the actual FM front end. Not sure how that is, but one step at a time. Let's get this thing ready for testing reception. It's been waiting around for a couple of weeks while I was on holiday, but since it's about 60 something odd years old, another couple of weeks probably didn't do anything badly to it, but it has done to my expectations. So what have we got here? I have fitted this tube. This is the IF amplifier, the EF89 tube. If you recall, this is what the original one looks like. It's all white at the top, and that's not a good thing. That means it's lost its vacuum and it's dead. Now, because these EF89s are quite common on German tube radios, I've got quite a few lying around, and I replaced that one there. The ECH81, the mixer oscillator over here, seems to be fine. We'll test it, see how it goes, and then of course I will do the actual restoration of that AM section, but it's always a good thing to see if we've got anything at all to start off with. I've connected the mini whip antenna to the AM antenna inputs here and ground. We'll connect the speaker to its output. I have the radio plugged into the lamp limiter isolation transformer. I've got the isolation on, so it's on the safety margin, the safety settings. It's not connected to mains earth. I have limit activated and I have this off for now. So it's time to switch it on. So what should happen when I switch this on? When I switch medium wave on, I'll put that on. I've got that on the one light bulb. Switch that on. That light bulb should glow because we know it's working. That one's blown. And that bulb should sort of go bright, then go dim. That's because the capacitor should charge. And then as current starts conducting through the tubes, that should go bright again as the current increases. And we should hear something from here. I've got the volume sort of on in the middle here somewhere. I don't even know where that is. It's at that end. No problem. Let's hit it. That's on, that glowed, that went dim again. It's drawing about 100 milliamps. No noise so far. And we've got sound. And that's going brightly again because the current's going up. We've got medium wave. Can we pick up anything? Yes, we can. Whoa, pretty noisy. Okay, we got reception, but it's pretty noisy, not very sensitive. Let's try long wave. Don't expect much on long wave at this time of the day anyway, but it's making the right noises. Let's try short wave. Short wave's dead. No, it isn't. Bloody hell, it's very quiet. have to be very, it's very difficult to tune here. Okay, it's receiving. Volume up, maximum. Let's give it a bit more power. I'm going to add the 60-watt bulb to it.
Didn't stop Russia. Here for us. Steve, tell us about the exit polls.
Yes.
Okay, well, the exit poll puts
fading in and out.
To get about 44% of the vote. That's more than...
But it is receiving.
Jugé involontaire l'obtenu pour l'Algérie en Coupe d'Afrique des Nations.
Not bad. Very, very touchy, the tuning. Very, very touchy. Okay. Okay, this thing's working. Right. The AM has got reception, which tells us quite a lot actually, and it also creates a perfect basis for the restoration portion of the work that I have to do on here. When we have something working and we haven't changed any of the capacitors and so on and tested some of the other components, it tells us we've got an easy way to do the restoration, and that is change a capacitor, go back, test it again. It's either going to be the same or better. If it's not, you know that change of that capacitor caused the problem, so you can go back and correct that. It's a fantastic and easy way to do the restoration. And it's the one I like the most. It's not the one I get all the time, but it's the one I like the most. So yeah, that's pretty clear cut what needs to be done now. And if we just look at the schematic, we can get a pretty clear idea of what it is we're talking about. Let's have a look at that. Right, so what do we have exactly? We have checked to the point where the audio signal comes in here. And we know that works because the pickup signal was working through, and all this orange stuff was the audio section. So we followed that through and that's working. Okay, so what we're doing now is we need to take off, we need to go back from this point, that point and that point, to find the audio coming from the radio sections. Now one of these is FM, the other one is AM. And you can see that when you switch, what is it, A1, 2, and 3. A is UKW, if you 1, 2, 3, 1, 2, 3. So 2, 3 is normally active, 1 and 2 is the one that's active when you flick it. So this one here, the bottom one, I think would be FM. Let's follow this resistor up here. And yep, this is the FM section because it's coming from this section of the EABC 80, the discriminator. And the reason we know that is it's got a fairly big electrolytic capacitor here, 2 microfarads. It's got a 4.7 nanofarad. So this section here is the FM, and that comes down through here, through the 3.3 meg to a 2.2 meg. And that actually has a potential divider, basically divides the signal, and then that goes in when you choose FM. When you choose AM, you've got a 3 active, which is that one there. If you follow that signal back through there, up here, this is a screen connection. That goes to there. There's a 270 ohm, 270k resistor to there. Then that goes, it comes from this point, from this IF transformer point. That IF transformer secondary is the one that receives the signal, and that diode there to the cathode is where the actual signal detection is done. So this bottom one here is the AM IF transformer. Okay, the top one would be the FM IF transformer. Brilliant. What you have here on the IF section is two diodes back to back. Effectively, this is the cathode, and this is the cathode, that's the anode of the one diode, and here you've got the anode and the cathode of the other diode, and this together with the capacitor there creates the detection stage, and it also gives you quite a convenient point later on to do the IF alignment. But we'll get to that. What we're interested in now is this section over here. This thing also, if you follow this line down there, it also comes through to, where is it? Down here, comes through to a 1 megohm resistor, through the 1 megohm resistor to a 10 nanofarad capacitor. Now this 10 nanofarad capacitor, if you follow that signal there, that level there, it goes across here through a 1 meg to the grid of the ECH81. That's the AGC voltage. So that decoding at the back there, up here, also produces an automatic gain control level voltage, which is negative. The more negative it is, it's a DC voltage, the more negative it is, it means the stronger the signal, and that is fed back to the grids of the tubes to control the gain of the respective tubes, so you get automatic gain control. On this tube, there's that voltage will be here. It'll go through that resistor, up here, up there, through those. These are DC voltages we're talking about, and through down here to this grid. So it actually goes through the pickup, the secondaries of the IF transformer we've had there. So that's the AGC. Now, the one capacitor that definitely needs changing will be this one here. Changing this AGC capacitor, this is sort of the capacitor that takes that AGC voltage and sort of filters it a bit, makes it more steady so that your automatic gain is not fluctuating at the speed of the audio. It's actually just fluctuating at a much lower speed to give alterations to different signal levels without the actual audio level affecting it. That usually requires changing, and that makes quite a difference then sometimes to the actual sensitivity, because if this thing leaks, it means that the control voltage that you want at the grid, the DC control voltage, is affected. Another thing that could affect sensitivity is actually the biasing of these tubes. This tube is biased, cathode biased, as you can see. There's a 100 ohm resistor and a 47 nanofarad capacitor here. We need to check those. That could be leaking as well, so the bias of this could be wrong. And of course that would affect how much signal you're getting through and how clear it is. The same applies here. This thing is also cathode biased. If you see, this is the cathode. You've got a 100 ohm resistor to ground and a 47 nanofarad capacitor here as well. So again, we need to check those. So these two capacitors and the resistors are also fairly good possibilities for improvement when we do the checking. Other than that, what do we know? We know that the front end, is actually working, because we're getting, this is the antenna over here, that's antenna ground antenna, comes through here, it comes in here, through there, through that coil. So this coil and that capacitor, it's meant to block out any 460 kilohertz signals coming in. In other words, the actual IF frequency gets blocked from coming in. You don't want signals coming in that are close to or spot on the actual IF frequency, because what you want to do is create the IF frequency internally. So this is the blocking. Then the signal comes through. There's that 1 nanofarad capacitor there, goes through that coil, gets picked up by that secondary, and this is a tank circuit, obviously, and that's 0.1. What is that? E1, and the middle is 2. E1, 2, 3. If we go down here, E is shortwave, E1, 2, 3. So when you select shortwave, 1 and 2 get made, and the connection between 2 and 3 gets broken. So that switch flips over to the top there, which means that this coil over here is for shortwave. That's a shortwave coil. So if you select shortwave, that switch is made. So your signal goes in here, in there, and it goes straight to the input of that ECH81, which is the mixer oscillator. So there's not much else happening here when you select shortwave. What happens when you select medium wave? When you select medium wave, when you don't select shortwave, the signal going into this point comes from the bottom here. And the bottom here has 2 coils and a preset capacitor, fixed capacitor. So 2 tank circuits. And what this is one of them. So H1, 2, and 3. This will be one of these would be the long wave, one of these will be the medium wave. If we follow H, 2 and 3, where is it? H, there we go, medium wave, H. That's those guys over there. So medium wave, that's a medium wave switch. And what this does is it's creating a pre-selection of the frequencies that will be allowed to go into the mixer. Because you've got that tuning capacitor over here, which is one part of the actual tuning cap. But you're pre-selecting which band of frequencies the mixer is going to be able to see to mix with the IF frequency, or rather with the oscillator frequency that this section is going to create. So that's what you're doing here. There's usually not much to change over here. These things are coils. You've got to make sure they're working. We know they're working actually because we've got the tuning working to a degree. But it's always good to check, and I will check that. You check for continuities and so on. So I will check that. There's only really one, well, there's those small, very small capacitors over here. These are the variables, small caps. They're usually fine. This one here might be off. This one is this one, 5 nanofarads. We'll see what type of cap that is. Check that resistor, and that'll be the front end done. This here, this tank circuit works in conjunction with the tuning on that part of the tuning capacitor, the AM tuning capacitor. And then the second part of the AM tuning capacitor is that one there, which operates on the other half of this section, which is the mixer oscillator, the actual oscillator. And that oscillator is this thing here, which also has some switching between whether you're listening to shortwave, long wave, or medium wave, to take you to the appropriate band. And then that part of the capacitor allows you to tune to get a different oscillator frequency. That frequency then goes to the where it comes out of here, there, and it comes out of here, there, and it goes into that. It goes into the ECH81's triode, and that frequency gets mixed with the frequency coming in from the front. The result is a number of signals here that are related to the 2 frequencies, the one you want to tune to and the one you're producing in the oscillator. One of those that you want is the difference, and the difference is 460 kilohertz, which I believe is the IF frequency of this thing. And that difference is filtered through the IF transformer when you adjust it for the IF frequency. So all the other frequencies gets wiped out with this filtering, and only the IF frequency, which is the difference between these two, gets through to that side, which is that's where your carrier is now. That's where your signal is. But we'll probably get to that just a little bit further. I want to do some checking on these bias conditions on these tubes and report back, make sure we don't have any major cock-ups here, and see if that's what's causing the low sensitivity. I'll also check the other caps, like that thing there. That's a 4.7. That's a contender for a possible paper cap. Let's see what else we have. Let me get started on this and report back. I like to sort of start and clean through the whole thing, make sure that we do this systematically. I've done a little bit of housekeeping here, a little bit of cleaning here. I've removed the faceplate and I decided to clean up the front. There's still some traces of dirt, so I'll probably have to go back into that sometime. I've cleaned up the switches and they cleaned up really, really nicely. This was just done with isopropyl alcohol and a toothbrush, an old toothbrush to scrub away, and then a lot of cleaning up with some things we're going to stop seeing soon, I think, because of the plastic. So you literally clean it off, every little speck. There's actually still a little bit of dust here. And when you want to clean between the switches, you just push it down and you get on that side and on that side, then you reverse it and you can get that side. So you go through this millimeter by millimeter, take your time, and the result is usually quite good, as was the case here. These switches are like new. Now, the faceplate, as I said, was in perfect condition, so I've moved that away. It's always a good idea to get it out of the way because they are the easiest things to break. This glass is, I don't know, 60 years old, and any little touch on that thing, it'll crack like crazy, and you cannot replace them. They're a pain in the butt to remake. You can do that. I've done that with one of them, one of my radios, at least one, the BRAUN ATELIER 3, which came with a cracked faceplate, and I actually redid the whole faceplate with Adobe Illustrator, and it was literally every single dot, every single spot, every line, everything was done on Adobe, and I got some guys to make the plate out of acrylic. I ended up with 2 layers of acrylic, a thicker one, the graphics behind it, and then a thinner one just to hold everything in place. But it really is a tiresome job. And I know there are people actually making faceplates in America, in the States. The ones I've seen are usually for American radios. I know they've done a few that aren't, but the majority of the ones that I've seen done are for the older American radios where you can actually buy a reproduction faceplate. I haven't found a place in Europe that offers that luxury for German radios, so I'm very, very careful with the faceplate. Now, we literally have to start off from the antenna input. Where does the signal come from? And then follow it through and follow the schematic, and doing exactly that which I've done with the B+ demonstration, where you literally follow every single line and measure continuity, measure resistance, in some cases measure capacitances. I'll take this one step at a time, and I know I'm doing this very, very slowly because this particular radio I decided to do it that way, literally go step by step and use it as a sort of tutorial series, which I could probably refer to in the future if I want to skim through certain tasks and say, well, if you want to see how I do that, go back and see video 3 or video 4 of the Rheinperle series. So that's the reason why this thing is going a lot slower. I know it can be a bit tiresome for some, but I always try to remember that I learnt most of my techniques in restoration from other videos, and one sometimes forgets that there are people starting off on the hobby right now. So some of the knowledge that you need to pick up, you literally have to go down to the basics. And I remember I needed those basics. I also remember seeing videos that were sort of skimming through too quickly and aimed at people who knew what they were doing already, and that was a bit frustrating for me. So I'm trying to sort of do a mix of some restorations that are more superficial, if you can call it that, and others that are more detailed. And this one, since I started off doing it very detailed, I'd like to carry on that basis. Anyway, let's have a look at the front end and see what we have. An interesting fact about this radio is that the entire front end, AM front end, in other words, where the RF comes in through the antenna, through the IF trap, is actually done on top of this. So all the coils that you see on that first section are actually done up here. You've got the various coils. There's a trimmer cap here. The actual connections to the switches then go down to the switching, and come back up. So the whole front end is really sitting on here, I think with no exception. There are quite a few components underneath here. You can see a resistor, capacitor, another cap, but everything is really done up here, which makes it quite easy to do the continuity checks, which is what we do to find out if everything is in order. So that was checked, and we went on then to the next stage, which was the oscillator section. What you're looking at here is the oscillator section. 1, 2, 3 coils, a variable capacitor. Sometimes in this section you'll see another variable capacitor, a trimmer. In this case we've got 3 coils, and those 3 coils happen to correspond to the coils in the oscillator section. Now, this is just a quick demonstration of how you can very quickly determine whether your oscillator is working or not. For the oscillator to be working, you need to be producing a signal which is, in this case, 460 kilohertz above your tuning signal, above the frequency that you want to tune to. Now, here we can very easily check that it's working, because you put the volume up and you get a change in the noise, even if you're not getting much reception. But if you just want to see whether the oscillator is working, it's very, very simple. Although for this experiment you do need an oscilloscope, and what you do is you connect the ground of the oscilloscope to the front pin and you put it over these coils like that. Now what it's going to do is it's going to detect the actual signal, and I'll show you what happens on the scope. As you can see there, we've got something, we don't know what it is, and I've got this loop over that first coil, and it's actually quite strong. If I go to the second coil, it's much, much stronger. If I go to the third coil, it's weaker. So this tells me that that middle coil is the one I've pressed, and it's medium wave in this case. Now if I change the time base of the scope, I get that. Now that signal is 90 millivolts RMS. It's about 260 millivolts peak to peak. It can be more, it can be less. You really are picking up an induced voltage here, an induced field across this loop. So the actual value doesn't matter. What it does allow you to do is, if you tune, you can see the frequency change. Now the faster I do it, the quicker you see the frequency change. And the frequency now is at 1.3 megahertz. If I go up that way, it's reducing, 1.2. And it actually changes in amplitude depending on what the frequency is that you're tuning to. Now, this means that, for example, if I go down to the minimum, there, that's right at the end, minimum frequency, 960. If I subtract 460 from that, which is the higher frequency, I know that I'm tuning to approximately 500 kilohertz, so right at the bottom, frequency-wise, of the medium wave band. But it does let me very quickly determine if my oscillator is working. So we know that here, the oscillator is working on medium wave. If I change this to long wave, look what happens. It just drops dramatically. Now, if I change this loop to the other coil, it doesn't really make that much difference, but it's a little bit bigger. And I can do the same thing. I can change the frequency here. 700. There's about 800 kilohertz. So that's my long wave tuning. Now if I go to short wave, I have to move this to the shortwave coil, which could be that one, but it happens to be that one, the last one, because that's the strongest signal. So I know that that's the coil in the shortwave section. If I change that, I've got 19 point something megahertz. And if I tune same thing, it changes. Forget about the amplitude because this thing's moving around, but if you look at the frequency, give that a bit more. Whoa, that's too much. 14 megahertz, 13 megahertz. So you see, you can actually get a very clear indication as to whether the oscillator section is working. And generally, when you move this coil around this general vicinity, you'll pick something up if you make the oscilloscope sensitive enough. You'll pick something up, and then you can just check what frequency it is and check whether it changes when you change the tuning. So we've seen here this oscillator section is working perfectly well, and as you've just seen in the painting that I've given you, absolutely nothing was swapped over here. Everything was within spec. There were no components that were either shorted, open, or otherwise. So we're good to go, or rather good to go on. And let's do so. And what we need to look for now is we need to check the bias circuit of the ECH81 and also of the EF89 and how that relates to the IF transformers that are connected between them. This is the result of the checking that was done. All the stuff that's in pink, the biasing of that tube was checked. All these resistors were absolutely spot on. That biasing was perfect as well. All the interconnects were perfect. As far as this part is concerned, it was possible to check the coils. I did not open the IF cans themselves to check the capacitors. These generally don't go wrong unless you get into tin whisker territory, but that's another story. Here we have the same thing on the secondary of the IF transformer, the AM band part. What we have here really is probably one of the first times that I haven't had to change the AGC cap. This one was measured perfectly. So we've got our signal, if you follow the pink lines, we've got our signal going to the switch where it switches between FM and AM. And that means that everything was done, and ironically, or unexpectedly, there were no components out of spec, shorted or open, which means I'm actually a little bit apprehensive as to what I'm going to find when I switch it on again to see whether there was much improvement from what we heard when I first powered it up, because generally when you have changes of components, you notice the improvement immediately. When you don't, then there's only two possibilities here, and that is the cleaning of the tube sockets, which obviously get done as you do the restoration, and which I've done quite thoroughly here, and probably more importantly, the cleaning of all the switching. Now what I do here is I pump in some contact cleaner and then flick these switches, activate the switches dozens of times, come back to them, leave it for a while, put some more contact cleaner, do it again, and usually that makes quite a difference. So the only thing that's left to do really is do a check or test of the AM to see whether we've got an improvement or not. So let me set that up and let's get going. Right, let's have a look at what the results of this work are. I've got it on shortwave.
And get the artists to come back and revive that place. A lot of people think that the best moments of Sudan and the revolution were the 50s.
القرآن الكريم هكذا نقلنا لكم على الهواء مباشرة من رحاب المسجد.
Un disco que tiene que estar en todas las historias españolas. Genial, muy bien hecho. Gong era un proyecto de Gonzalo García Pelayo. Este disco
1000亿元资金，加快推进职业性提升行动。
And that side of the band is usually quieter this time of day. Let's try medium wave.
Los dos se juntan, hacen una fiesta, unos pagan las vacas, hoy en día pagan el dinero, ¿no?
Esto generaban estas conexiones neuronales en nuestro cerebro. Las empresas no le... preparar.
It's much, much better. Long wave. Very noisy in this in the workshop. Right. Conclusions. It's much, much better. And I think it has to do with the switching, the cleaning. This is still not the optimum time of day for AM. It's mid-afternoon, but I expect in the evening it'll get a lot better, but we'll be able to see that when I finish the radio and we do the final checking. I'll do a demonstration of this at optimum times. I'm happy with the result. I think the cleaning up really of the switches and the tube sockets has had the desired effect. Because no components were actually found to be faulty in this section, I can't really say it was because of the components. So yeah, sometimes all it takes is removing tubes out, cleaning the sockets and cleaning the switching. But having gone through this meticulously and done this in the traditional way, as I call it, I'm happy that everything's been checked, because sometimes you do change one component and find something dramatically improves. Well, this wasn't the case, but it wasn't too bad to start off with. And now we've got the AM done. And so that means we've only got the FM to do. And the FM, the only thing I need to do to test the FM is to put a tube in there. My concern is that the tube will draw too much current and heat up that resistor. So that's the first thing I'm going to focus on when I come back with the next video on the FM restoration. And I hope you've enjoyed that. I hope you've learned something. I certainly have, as usual. And if you like this video and you have got something from it, please subscribe, share, press like and all that jazz. And I will see you back soon. Thanks for watching. Bye for now.